Happy Friday, everybody, and welcome to the last episode of Daily IoT for the week. We're going to wrap things up with this circuit in front of me that I am super excited to talk about. This, if you recall from a few episodes ago, was the circuit I was trying to build and talk about, but was unable to because it didn't work. It's going to be a short one because I can't get this freaking thing to work. Well, now I have got the parts in from Mouser, just an analog voltage comparator that I was waiting on that came. I swapped out my Radio Shack one for this one, and the thing works like a dream now. And so I want to talk about it really quickly and why I find it so fascinating. I got this out of the Art of Electronics when reading about RC circuits, resistor capacitor circuits. When you connect them in certain ways, they have very predictable behaviors based on the physics. And what we've done here is we've connected a capacitor and a resistor in parallel. We're going to charge up the capacitor when we press the switch, and then allow the capacitor to drain through the resistor and the voltage will come down. Now, that will do so in a very predictable manner, and it is an exponential drop-off. This, again, is because of the physics of how these things work. And so it will charge up to 9 volts, that's the system voltage, when I press the button, and then when I let go of the button and remove the 9 volts, it will decay exponentially, very predictably, back down to 0 volts, based on the components I've chosen. Now, this rate of decay operates on what's called a time constant. And that is simply, in this circuit, is the resistance times the capacitance will give you your time constant. And then based on the equations and the integrals and all this solving, you don't have to understand the math. All you have to know is that it will take a certain number of time constants to hit certain voltages. So once you know the time constant, resistance time capacitance, you know how long it will take to get to any voltage along that exponential curve, which is pretty interesting when applied like this. We're going to set a reference voltage on our voltage comparator. For those that don't know the way a voltage comparator works, it has 2 inputs and 1 output, and then a power and ground connection. And you supply it, in this case, with 9 volts, and then we create a reference voltage. And when the input voltage, the other voltage, is above that reference voltage, the output is turned on. When the input voltage is below the reference voltage, the output is shut off. Simple digital on-off state. Why that's interesting is that we can set the reference voltage to anything we want, and I have done so with a potentiometer voltage divider to a very specific voltage based on what I know about that time constant exponential drop-off of my RC circuit. And so in this case, it's set to 1 divided by E being a constant, which works out to be about 37% of 9 volts. And by doing that, that's very intentional. By doing that, I know that once the capacitor is charged and I remove the voltage, it will take exactly 1 time constant for the voltage to drop back down below that voltage reference value. And so it makes the math very simple. Once I press the button, it will take 1 time constant, the output's going to turn on, and it will take 1 time constant before the output turns back off. R times C, and I've chosen R and C to give me approximately, theoretically, 47 seconds of on time for the LED, which is what's connected to the output. So I press the button, the LED turns on, and it will not turn off until we hit that theoretical value. Now, it's not going to be exact because the resistor's not perfect. There's tolerances and percentages that it could be off. Same thing with the capacitor. So in a purely theoretical, if these were perfect components, it would be 47 seconds. I've timed it somewhere around 42 seconds is what it rings in at. But you can get this down to pretty tight. You're not going to be microsecond, millisecond times on these, but seconds. You can be right in there, very tight by choosing the components, and you can even adjust them to get the exact time, and then it will perform exactly the same every single time you press that button. That was good timing. Turned off right then. I love this circuit. Why do I love this circuit so much? So the book talks about some examples. Don't think of it as a circuit on a breadboard. Think of it as the input, instead of a switch, being a coin, the output being turning on an air compressor, like a gas station, coin-operated air compressor. You get 1 minute of air and then it turns off. Think of it as the end of cycle of a dryer, that buzzer that goes off for 4 or 5 seconds. One of these, the input is a signal that the cycle is over, the output is turn that buzzer high for 5 seconds and then turn it off. The reason I'm so hung up on this circuit this week and why it has my mind a little bit blown is that nowadays we often reach for the platforms. We grab an electron, a photon, a Raspberry Pi, an Arduino, and we solve simple problems like this with a sledgehammer, which, don't get me wrong, I love the sledgehammer. Love me some sledgehammer. But there's some trade-offs there, right? So let's say I was doing this with a Raspberry Pi and I wanted to make my end of dryer cycle buzzer with a Raspberry Pi, because I got a Raspberry Pi in my dryer because it's super fancy and cloudy and stuff. Well, now to turn that buzzer on and off, I can use a GPIO pin on the Raspberry Pi, but I have an entire Linux operating system running to make that happen. Any number of things could go wrong in the operating system, in my firmware and programs that I have running that could cause this thing not to turn on reliably, or once the buzzer turns off, not turn off reliably. And so there's things that can go wrong. Even with something as simple as an Arduino that's not running an entire operating system, you're still running firmware. And while those are a lot more predictable, there's still a lot of things that could go wrong that would upset the behavior of your circuit. This does not have those problems. Basic physics is running these, and so the only failure point of this circuit is if the components were to go bad. And so the resistor burns out, the capacitor explodes, something like that. But remember, these things have very good durability. Think of that Kenwood stereo that I took apart a couple of episodes ago. That thing has capacitors and resistors all over it that have been running flawlessly for 20 years. And you never need to reboot it, you never need to patch it or run updates on it, or solve zero-day exploits. This is just simple discrete components that create a very predictable outcome over and over and over forever. And I think that that's pretty powerful because, like I said, oftentimes we reach for the sledgehammer when if we had some knowledge and expertise in basic electronics and how to create and construct circuits like this, we could harden the designs of our projects. This is something that if we might control, the input might be the output from an Arduino, just a little pulse that does this. But from that pulse on, I know that that circuit's always going to work and I don't have to worry about it. I can put it in cruise control. And so I think there's something very powerful to that and just something to think about when we're making projects. Now, this is a lot higher overhead. You've got to design the circuit and construct it, whereas with this, it's all together. You just write the firmware and push it. So there are trade-offs. This is much cheaper, a lot cheaper to signal an end of dryer cycle signal with a circuit like this than with a full platform. This, you can't update over the air. You set this for 42 seconds or whatever it is, and you decide 3 months later, the back office decides we need to change it to 37 seconds. Well, you can't do that. You can do things like stick potentiometers in there instead of fixed resistors, so you could use like a screwdriver to adjust the time. But anyway, there's some trade-offs like that, but there are some applications where that kind of updatability and adjustability are just not necessary or as necessary as we think, and this is a much more tried and true solid way of accomplishing those things. So just something to think about. I've like I said, I've really been thinking about that this week and just wrapping my mind around solving bugs, and I write a lot of software for a living, and just the simplicity and beauty of this is striking to me. So I wanted to share that with you. That's it. We're going to wrap it up there for today's episode. I am going to be working on the scooter project tonight, trying to get the LED strip switched over to the Electron and connected up to the scooter. If you want to follow that, you can check me out on Instagram. I'll be posting updates to my Instagram story. I'm not going to put any footage in today's episode or film it. And so check that out if you'd like to. And hopefully I'll have some good demo stuff to show. But that's it. I appreciate everybody watching. I hope you've had a fantastic week. I hope you have an amazing weekend. And thanks so much for watching Daily IoT, the show where together we're learning how to make the Internet of Things one day at a time.